Okay, hello everyone. We are going to do some of the week 8 material. So this is about the long promised integration of one form's long curves. And we're going to sort of write that down. Section 2.5, integration of one forms over curves. So again, just to remind you, physically, we're taking inspiration from the idea of a force field. So a field that tells you, so a function that tells you at every point something like a vector that is a force that operates in that direction. Really, it's not going to be a vector, it's going to be a one form. There's going to be a way that we can convert velocity vectors, so small amounts of displacement in a small amount of time, to amounts of work that we can then add up over the rest of the curve. So that's the sort of classic example. But you could also think of gravity acting. So to create a weight, and then that weight will be like a vector, and you can take the sort of component of it in a particular direction of whatever your speed is, your velocity, and then you can work out what the work would be done to oppose gravity. So if you were trying to lift off a rocket, for example. Okay, so I'll just write some of this down, not all of it, but in section 232, we saw how to make one forms out of zero forms. So remember, zero form is just going to be a function. This is going to be something that tells you at every point what a some number, and then you can differentiate it in the direction of a vector. So that could be a vector field, that would be something at every point, or it could be the velocity vectors along a curve that would only be defined at certain points. Right, so we're going to consider integration of one forms over curves. It is going to be much easier to make sense of that. You can integrate two forms over surfaces, a bit like kind of creating an area. But let's just let omega be equal to g1 dx1 plus g2 gm dxm be a one form, and gamma sending a b into a to the m, a parameterization of curve C. So we can apply omega to the parameterization gamma by evaluating the point gamma t with velocity vector gamma dash of t, and then we will get something. So there's one form. Well, you need to know what point you're at. So that's the gamma of t part. And you also need to know, because that tells you how big what the one form is at that point. And you also need to know what velocity you are going. So how fast and in what direction. This is the one form at the point P, and you've got dxi, which we're thinking of as a function on tangent vectors of gamma dash of t. By definition, what this is the sum of gi, again, just at the point gamma of t, times gamma I dash t. So it just picks out the ith coordinate of that function. Right, so note that if omega is actually equal to the differential of some function of a zero form, this is the directional derivative of f at gamma of t in the direction gamma dash or t. So let's have a definition. This is the integration we're after. So this is integration of one forms over curves. Let omega be equal to, we've got these and the coordinate functions of this one form. And let gamma be from A to B, this interval, be a smooth regular. We haven't really discussed this, but it's not something I want to go into. You can forget this word of C. Then the integral of omega over C is, so we write it as an integral sign over the curve of W, omega rather. So that's all we write, this integral. And it's going to be this particular expression. So the value of the one form at the point gamma of t, and what it gives you after application to the vector gamma dash of t. We've already written down what these are in terms of the coordinate functions of omega. We get the integral from A to B of the sum of the gi gamma 1 of t up to gamma n of t. So just splitting everything into coordinates times, put that together, times the gamma I dt, right? And then dt. So just a quick remark, 2.49, you may define this over open intervals as well. So this is defined in the same way for open intervals. Because if you're removing a finite number of points from a curve, then you're not going to affect the integral. That's just an infinitesimal amount or difference, so it doesn't change. So as we're moving a finite number of points, do not change the integral. Okay, well, we need to have an example, don't we? And I think actually doing this in practice is a lot easier than trying to understand the concepts. So concentrate on this part. The last bit make too much sense. So consider the one form, omega is x dx plus y dy. Okay, so what it's doing is it's this one form, as you get further and further away from 0, it gets bigger in both coordinates in the direction that you're going. Sort of radiates out, so you're getting a sort of stronger force away from the center. And the curve, we're going to integrate over is just going to be this one, a quadratic, a parabola rather. So points x, y, a2, such that y is equal to x squared. 0 less than x less than 1. Okay, so let's just plug everything in to this formula here. So these g1 here is x, g2 is y. So we have to apply those to the point x, y for each x, y we do. And then we have to find this derivative, which involves us obviously having a curve and then integrating as we get there. So let's choose a parameterization. So let gamma take you, and I guess we'll call it gamma 1 because it's consistent with the notes that we've been writing so far. So it's going to take the interval 0, 1 into a squared, and it's going to take you from t to t squared. So we're just letting t equal to x here, and then get that parameterization. So let's differentiate this to get the gamma 1 dash of t. That is just going to be 1 2t. So at every point on the curve between t is 0 and 1, so we should say 0 to 2 to 1, we are going to get a vector which has velocity 1 and 2 times t. So it's getting faster as it goes further along the curve. Okay. So we have to plug in to the formula. So we have to take, first of all, the integral from t equals a to b, and that's 0 in this case to 1, of the sum of the different gi's. So those are these functions coming from the form. We'll just zoom out a bit. Those are these functions coming from the form, here, so G1 and G2 applied to the point, which would be gamma of t. So we get t times the derivative of gamma I of t along the x direction, which is here just 1, plus the other part, which is y. So G2 is y, which is t squared, times the derivative in the y direction, which is 2t. And that's dt. And so if you do that, you end up with t squared over 2 plus, that's 2t cubed. So that'll go to 2 to the 4 over 2 between 1 and 0, which is equal to a half plus a half, and that's 1. Okay. So let's continue. One of the things that is not clear when you look at, so the integral of this one form over a curve requires you to have picked a parameterization. And there are lots of different parameterizations. And so what we want to know is that it doesn't depend on the parameterization we pick. And up to orientation, that is true. And we're not going to prove this theorem, but I'm just going to state it, which says precisely that it doesn't matter which parameterization you pick. So theorem 2.51. Let's see the oriented curve. Again, CB an oriented curve, which means that you picked a direction for it to go along. So there's some parameterization that you've chosen in the right direction. Then the integral omega c on omega along the curve of omega does not depend on the parameterization of C. So you can choose any gamma that traces the thing out in some smooth enough way. On the other hand, if C dashed is same curve but with the opposite orientation, then the integral over the curve that you get from first orientation is equal to the negative of what you get from the second one. So we'll test this out, this theorem, and that will do for us rather than a proof. So let's do that. Example 2.52. So we're going to pick a new parameterization of C and see what we get. So this is going to be gamma 3, taking 0 over pi over 2 to A2. That sends t to sine t sine squared t. So if you remember the original equation, it was just a parabola and it just had the property that y is equal to x squared, which is still true here. And as this interval goes from 0 to pi over 2, sine will go from 0 to 1. So it does give you exactly the same curve. We want to know that the integral is not going to change in this case. So we'll just do exactly the same thing as we did before. We're going to differentiate, apply the one form, and integrate. So we get gamma 3 dashed of t is equal to, if I differentiate sine, I get cos. If I differentiate sine 2t, I get 2 sine 2 cos t. And now if I get the integral around the curve, I just have to plug in the values of gamma of t to get my one form, and then apply it to my velocity vector. So the integral around the curve is going to be equal now to the integral from, this time we're going from 0 to pi over 2. So the one formula is x dx, so that's sine t. And then I have to apply that to the derivative here, cos t, and then the y was, so the coefficient of dy was just y again, so that's sine squared t, and then the derivative here is 2 sine t cos t t. So we're going to do the following. We keep the sine t cos t, and we're going to replace this with 1 minus cos squared. Sine t cos t, 1 minus cos squared t, and 2 sine t cos t. Which is going to give us 3 sine t cos t. We take a 1 from that bit and my 2 sine t cos t from here. I'll do these around here. Minus 2 cos cubed t sine t. So the reason for doing that is that you can now integrate cos by increasing the power and dividing by it, because then it will suck in the sine t. So let's just write it down. Similarly here, we can get, we can turn the sine t into sine squared t and suck in the cos. So 3 over 2 sine squared t minus, let's increase the power there and divide, we get 1 over 2, which is 2 over 4, cos to the 4 t. And we just need to make sure that we put the plus there as well, because when you differentiate cos, you get sine, so the minus will come out. And then you have to apply that between the limits pi over 2 and 0, and we hope very much that we get the same value. So when I apply pi over 2 here, I get 1 from the sine, and I get nothing from the cos. So that gives me 3 over 2. And when I apply 0 here, I get nothing from the sine, and I get a half from the cos, which is, 1. as we are hoping. So we do get the same outcome with the different parameterizations. As you could see, it was a lot more complicated to integrate this particular along this particular parameterization of the curve, and there's usually a simplest one you can pick, and that is always a good piece of advice. Okay, final example for this section, and then I'll stop the video, is going to be example 253, which is just going to be doing exactly the same thing, but where we take an opposite orientation. So let's parameterize C backwards. So we're going to take gamma 4, which takes same interval 0, 1 into A2, but where T maps to, and this is always the trick that you can use, if you take the end point and then do 1 minus the beginning point, you will get something that runs backwards. And then 1 minus T squared. So again, we've got the same curve because we want to know that y equals x squared, which it does, and that we get the same values of x and therefore y occurring. And we do because we're just going from 0 to 1 this way, 1 to 0 that way, and they are the same. Right, let's compute the integral again. We're going to do gamma 4 dash to t, and that's going to be equal to, this time, -1. And if I differentiate here, I get 2 into 1 minus t times -1, because I get to differentiate inside the bracket 2. Okay. And I'll just write this down again, just in case we've forgotten. X, one form we're looking at is x dx plus y dy. To do that integral along this new curve here, we are going to plug the point that we're looking at into the one form. So that's 1 minus t, and then we want the speed in the x direction, which is going to be -1, plus the value at the point y of the one form, which is 1 minus t squared, equal to y, and then times the speed of gamma in the y direction, -2 times 1 minus t, and then plus a dt at the end of that. Right, so let's just expand all that mess out. Oh yes, what do we get? We're going from 0 to 1 here. That's 0 to 1. And we've got t -1 plus, if I expand this, I'm going to get -2 into, and I'll just do the 1 minus t cubed, which is 1 minus 3t plus 3t squared minus t cubed dt. Two t cubed. The squareds, we've got -6t squared. For the t's, we've got 6 plus 1 is 7t. And then we've got -1, -2, which is -3. And we have to integrate all of that dt, again, from 0 to 1. And if you do that, add 1 to that, divide by the power, you've got t to the 4/2, and then just going along, you've got 2t cubed, and then you've got 7/2t, and then you've got 3t. And then we do that between 1 and 0. Rather disgusting calculation. But anyway, we've got a half minus 2 plus 7/2 minus 3 minus what you get at 0, which is just 0. So we just have to add these up. 7/2 plus a half is 8/2. 8/2 is 4, and 4 minus 5 is -1. And that is exactly minus the first curve that we had, where C tilde represents the original orientation.